hour probably. We are starting the very last chapter today. Pretty excited? The part of the chapter that we're covering today is pretty well connected and to like the chapter 6 stuff that we're being tested on. So I think it should, some of it at least should be a nice kind of refresher in seeing how some of the stuff we've been learning in chapter 6 will, can be used to help us out. What? Pete.
This is.
Yeah.
We're going to do this first section today. Thursday we're taking a test. We're turning in the problem set. It's not due until Friday, but certainly if you have it done by tomorrow, I'm happy to take it then.
Are we going to have any time to work on it today?
It depends on how long it takes us to get the material done. We had lots of time this morning in recitation, but there were like just 3 of us that came, so.
Cool.
Actually, do
You know,
have a copy
the only
of
ones
the
that are
problem
from-
set? I looked where I had mine this morning. It wasn't there. Thank you.
And then next week, we're going to finish this chapter on Tuesday. We'll have the week's recitations and Thursday's class to work on a practice final exam and get ready to take the final exam, which reminds me to, if you haven't done so already, there's a link here at the bottom of the top module where you will choose which day to take your final exam. You have to provide me. I'm just using Google Forms, so you have to write your first and last names, and then pick one of the days. There's a Wednesday at 1 or Saturday at 10 option. Okay. Are we ready? Yeah. All right. So we're working with quadratic equations in this last chapter. We're working with quadratic equations in this last chapter, and a quadratic equation is one in which the highest power of x is x squared. You have an x squared term. You may have a linear term. You may have a constant. The only requirement is that you have at least this x squared term. There's no higher powers. You're not dividing by x. There's not, not radicals or anything. So it's one that can be written in this form. You might not be given an equation in this form initially, but if you can rearrange the terms so that it can be written this way, it's quadratic. So here's a quadratic equation. This is also quadratic because we could rearrange it to look like this. There it is in that form, where a, b, and c are 3, 12, and negative 18 respectively. Or if you zapped everything with a -1, it would look like this, right? When it's set equal to 0, you could just flip all the signs. It's still quadratic. There are 3 techniques that we have for solving quadratic equations. Factoring, completing the square, and the quadratic formula. I'm going to say something right up front. I do not care. I could not possibly care less if you all remember what the quadratic formula is, if you commit it to memory or not. I will never, ever say, use the quadratic formula to solve this on a quiz or a test or the final exam. Memorizing a formula to me is not very useful. We're going to look at solving by factoring today. On Tuesday, a week from today, we'll look at completing the square, which is so useful. That is an infinitely useful thing to be able to do. It is one of my favorite things to do, ever. I could do it all day long and be pretty happy for the rest of my life. And then we will cover the quadratic formula. In fact, we'll derive the quadratic formula together. We'll see why the quadratic formula works. But I want to make sure that everybody understands that you will be asked to solve by factoring. You will be asked to solve by completing the square. I will never ask you specifically to use the quadratic formula. So please, whatever notion you might have of just saying, I know the quadratic formula, so I don't have to worry about these, like, dispel that, like, get that out of your mind. We're going to look at solving by factoring today. So this is the basic principle behind solving by factoring, and that is that if you multiply two things to get 0, like if their product is 0, then one of those things has to be 0. That's the only way you can multiply two things and get 0. So if you are solving a quadratic, first of all, if it's set equal to 0 and you can factor what's on the left side, then you could basically boil that equation down to two like linear equations. So 3t squared minus 2t equals 0. It's set equal to 0. That's the first check. Make sure it's set equal to 0. And then, can we factor the left side? Does that left side factor? What can we do?
Take a key.
Yeah, take out a t. So if I take out a t, what's left? 3t minus 2. Now I haven't finished this step because this is still equal to 0. The fact that that product is equal to 0 is what lets me take the next step. And so here we are multiplying two things to get 0. Using theorem 7, that means that either t is equal to 0 or 3t minus 2 is equal to 0. So there's one of our solutions, t equals 0. The other solution we'll get by solving that linear equation. So if I add 2 to both sides, we get 3t equals 2, and then we can divide by 3 and get t equals 2/3. Fun? See, if you can factor, you will be happier for the rest of your life. That encourages happiness forever onward. No joke. Let's try another one. This one's already set equal to 0. So our next step is, can we factor the left side? Say that again, Aiden?
X plus 2, X plus 3.
X plus 2, X plus 3. So we need an X and an X to get to 2. 6 is either 1 and 6 or 2 and 3. They both have to be the same sign to give us a positive 6. And then the ones that end up giving us a plus 5x when we FOIL it out are plus 2 and plus 3. So, so now this product is equal to 0, and that allows us to invoke the fact stated in theorem 7. So then that means that either x plus 2 is 0 or x plus 3 is 0. And these are, of course, pretty simple to solve now. X equals negative 2 or x equals negative 3. Those are the two. Those are both solutions. We'd say, if some people get confused with the semantics a little bit. So if this product is equal to 0, that means that either x is negative 2 or x is equal to negative 3, which means that x equals negative 2 and x equals negative 3 are both solutions to this equation. Fun?
Yeah.
Yeah? Okay, good. All right. What do you notice about this problem? There's a 2 on the other side and not, and what do we want on the other side? 0. Yeah, so let's just start out by subtracting 2. All right, so we're not going to worry about factoring yet, right? The only time we're going to start worrying about factoring is if it's set equal to 0. So then we get 2x squared minus 7x plus 3 equals 0. What do we do now? Factor. And this is one of those unfoiling ones, right? Because it's a trinomial, so we're going to see if it'll unfoil. May not be quite as simple as the last one, but it won't be too bad because both our leading coefficient 2 and our constant term 3 are both prime. So We know we need a 2x and an x, and then we know we need a 3 and a 1. Either both positive or both negative, because we get a positive 3. We're just not sure which ones and where they go yet. Hayden.
It's negative. It's 2x minus 1 and then x minus 4.
And an x, yep. So let's do a quick check. So this is minus x, and that's minus 6x, and that does give us the minus 7x that we need. Good. So if it factors this way, now we have a product set equal to 0, what are we allowed to say?
2x minus 1 is equal to 0.
Yep.
And plus 3 is equal to 0.
Mm-hmm.
Is it supposed to be x plus or x minus?
Oh, yep, minus. And now these are both linear equations, so solving them is no big deal. So we have 2x is equal to 1, which means x is a half. Or x is equal to 3. I'm going to pause there for a moment and see if there are questions. Okay, let's do another. Is this quadratic?
Can be.
It can be. So what would you do just to see if it's quadratic?
Yeah.
Distribute this x. Okay, so let's start there. So we get 5x squared equals 7, and then we'd have plus 11x minus x squared.
Just write it the other way around.
Sorry?
I just wrote it as negative x squared plus 11x plus 7.
Sure, yep.
Could you minus 5x squared from both sides?
Yeah, so you're saying let's have it be equal to 0. Sure. So then we get 0 equals 7 plus 11x minus 6x squared. Now, there's a couple things. When I'm factoring, certainly this is a trinomial, and we could start by just trying to factor. I don't know about you, but I have this mental block in my mind. If my leading coefficient, and by that I mean the x squared coefficient, is negative. Like, I don't know. It just makes it 10 times harder, even though it shouldn't. So what I usually do is I rearrange this, because I also like to start with the x squared term, and multiply through by a negative, so I have a positive coefficient. So if I multiply by negative 1, then we still have 0 equals, and then we have positive 6x squared minus 11x minus 7. Now the 7 is prime, so I know I'm only going to have 7 and 1 for those terms, the second terms in those parentheses. 6 is composite, so we have a couple options. It's either 6 and 1 or 2 and 3, and we might have to just try a few things first. So Pete says it's 2 and 3, so 2x and 3x. Now one of these is going to be, I mean the last term is a negative 7, so one's going to be a plus and one's going to be a minus. It might not be entirely obvious which.
It's going to be 2x plus 1 and 3x minus 7.
Plus 1 minus 7. So let's do a quick check. This is plus 3x. This is minus 14x, which gives us minus 11x, and that works. Good. How's that so far? What do we get to do now?
2x plus 1 equals 0, or 3x minus 7 equals 0.
Yeah.
Solve that.
Great. Right, so these are simple equations. In the first one, let's see, we'll subtract 1 from both sides. In the second one, we'll add 7 to both sides. 2x is negative 1, or 3x is equal to 7, and on both of these we just do some division. We get x is negative a half, x is 7/3. I've got 3 more examples I want us to do. These are not in the packet. So I'm gonna have an additional sheet.
Is it?
Oh, great, thank you. So we got 3 examples of varying levels of difficulty. Oh man, you know what? I didn't I didn't print out this sheet to OneNote, but that's okay. I'll just write them down. Add a page. Okay. So example 1. The first example is x squared minus 6x plus 9 equals 0. This is sort of a run-of-the-mill solved by factoring. In fact, the factoring is not too bad. It's a monic polynomial. The leading coefficient is 1. How does this factor?
X minus 3, x minus 3.
X minus 3, x minus 3. So the solving isn't too bad. And what this leads us to, right now if we invoke theorem 7, with the 2 equations we get are that x minus 3 is equal to 0 or x minus 3 is equal to 0. And this, of course, unsurprisingly, gives us one answer, right? Either x is equal to 3 or x is equal to 3. I'm pretty sure that means x is equal to 3. So in the examples we've done so far, we've found 2 solutions to each of those quadratic equations. Sometimes there might just be one solution, and that happens when your quadratic factors is just 2 of the same factor. Like this is basically a perfect square, right? It's x minus 3 squared. In the second equation, yeah, so let's notice something first. That equation is not quadratic. Why is it not quadratic? Oops. Yeah, x squared is not the highest power. But the premise that, the theorem 7 that says if you multiply 2 things and get 0, then one of those things must be 0, you can extend that to however many factors you want. If I multiply 3 things, like if a times b times c is equal to 0, then one of those factors has to be 0. Or a, b, c, d. Like if you're expressing one expression as a product of things and it's equal to 0, then the only way that happens is if one of the factors is 0, no matter how many factors there are. So Pete just said, oh, we could take an x out. So we could start by taking an x out. If there were not an x in each term, if they're not a common factor of x, we'd have kind of a hard time solving this. But there is, so we'll take that out. We end up with 2x squared plus 7x minus 15. And then we can keep going. We can factor this quadratic. So we have a linear factor x times the quadratic.
2x minus 3, x plus 5.
2x minus 3, x plus 5. So quick check. Minus 3x plus 10x gives us the plus 7x. So now this lets us break this down into 3 equations. This means that either x equals 0, or 2x minus 3 equals 0, or x plus 5 equals 0. X equals 0 is just one of our solutions. Yeah?
Are you going to have the same amount of solutions as your largest exponent every time?
Well, it depends. If we only consider real number solutions, then you will either have, then no, not always. With a quadratic, if we only look at the squared, the highest power squared, like a proper quadratic, if you limit yourself to only real number solutions, which we are in this course, you'll either have 0, 1, or 2 solutions. It's possible to have no solutions. And we'll see examples of that happening in the next sections. However, if you allow yourself to consider complex solutions, like imaginary numbers, then yeah, there are always the same number of solutions as the degree of that polynomial, like the highest power, as long as you count them, we say, with multiplicity. Like, for example, up here we would say x equals 3 appears twice, so if I count that twice, then there's 2 solutions, even though there's one distinct solution, right? And next, if you're taking pre-calc 2, we're going to spend a bunch of time on complex numbers.
Oh, yeah.
It's great. No, it's great. That fact that says, like, in a polynomial degree n, we'll have n solutions if you include complex numbers and count with multiplicity is called the fundamental theorem of algebra. So it's, a pretty important result. So now we can solve these linear equations. So 2x equals 3, dividing by 2 gives us x equals 3 halves. And over here, x equals negative 5.
And x also equals 0.
X equals
Yep, I already boxed that.
Oh, I didn't see
Yep.
that.
So those are our 3 solutions here. So that was not a quadratic, but we got to apply the same principle. The next solution, also, the next example, also not quadratic. You leaving us already, Abhishek?
Forgot an assignment.
Okay.
I gotta run.
This is definitely not quadratic. I got x's in the denominator. It certainly doesn't look like one of those forms. But we do know, we just spent a bunch of time working with how do we solve equations like this. How do we solve equations like this?
lowest common denominator.
Okay, so what is the LCD?
X plus 2.
Say that again.
X plus 2.
That's included in the LCD. I'm sorry?
And then multiply that by
Yeah, so x times x plus 2. X and x plus 2 are relatively prime, right? They share no divisors in common. So we need to grab them both. This, of course, the denominator is just 1, so we don't need to grab anything there. So then we're going to multiply all terms by x times x plus 2. This is an equation, which means I do have both sides of an equation. And that's where I multiply everything through by the same thing. That is different than if we were just adding or subtracting fractions when it's not an equation and we don't have both sides. Right? I'm pointing that out because they're on the quiz you got back. I saw that mistake a few times, like wanting to treat the subtraction problem as though it were just an equation, multiplying the whole thing by the LCD. But we don't have both sides of the equation. If you're just doing the addition and subtraction, your only option is to multiply the top and the bottom of any given fraction by the same thing, right, to get to an LCD. Here, because it's an equation, our goal is to cancel out all denominators. So we could do some canceling here and here. And then what we're left with is, this is 2x times x plus 2 minus x plus 2. I'm keeping the parentheses because I have to make sure I'm subtracting that whole thing. And on the other side, just 3x, I think. Okay. What now?
Distribute.
Distribute that 2x. And then I'll also distribute the negative through. Okay, so we get 2x squared plus 4x minus x minus 2 equals 3x. And now we see this wasn't a quadratic equation to start with, but solving it will boil down to solving this quadratic. So sometimes quadratic equations crop up in our efforts to solve other equations. I'll subtract 3x. So we have 2x squared. Let's see, 4x minus 3x minus x. The x's are all gone. And then we have minus 2 equals 0. And if we're solving by factoring, which is kind of what we're doing in this section, let's try to factor this. There is a common factor we could take out first. Take out that 2. And the x squared minus 1 will factor. So we have 2 times x plus 1, x minus 1. So here's a product of 3 things that's equal to 0. And that will happen only when one of those 3 factors is 0. Now 2 is never 0, so I don't have to worry about that. But these other 2 factors can be 0. So x is -1, x is 1. Those are our 2 solutions.
Do we not worry about that too because it's not cubed? Is that the logic?
The reason we don't worry about this 2 right here.
The one up above, we had the x. We worried about the x. But that's a cubed.
Well, it's not. That's not what made us worry about the 2. I mean, 2 is not a. There's no. 2 is not a common factor to
No,
everything.
no,
We
no. I'm
didn't-
saying the x though. It was on the outside of the parentheses.
Oh yeah, yeah.
Or
This
down below, we
so-
have a 2.
right.
Is
So
on
like
the outside of the parentheses.
right, but
but
2
that
is
doesn't
2 is a
equals-
constant. Yeah, 2 will. For what value of x is 2 equal to 0? None of them.
Mhm.
For what value of x is x equal to 0? At 0. Yeah. Before we kind of put this away, I want to just take a look at this this part here. Right, so I could look at that as just the product of 2 things. 2 times x squared minus 1 equals 0. 2 is never 0, and so that means that x squared minus 1 is equal to 0. This is going to lead us into what we're going to look at on Tuesday when we do the next section. But another way to solve this equation is to say, well, let's add 1 to both sides. And then x squared is equal to 1. And if I know what x squared is, how do I get x? Say that again? Square root. We'll square root both sides. Now here's the thing. A lot of the time when we've done this so far, it's been in a setting where we knew we were looking for like a positive. Like when we use Pythagoras, for example, like we know that the length of a side of a right triangle is just going to be positive. But generally, whenever we're the ones to impose a radical on an equation that's not already there, we have to consider both the positive and negative roots. Right? There are 2 square roots of 1. They're 1 and -1. And so this is another way to solve this equation, that x is plus or minus 1. We have to make sure we consider both of those. This idea that we have this perfect square that's equal to a constant, and that allows us to like take a square root to get rid of that square, is the idea behind completing the square. Like, if we have a perfect square, taking the square root to get the solution, not like that's pretty simple. We've done that a bunch. When we complete the square, what we're going to be trying to do is say, oh, this doesn't look like a perfect square at all. How can I make it look like a perfect square? That's why we call it completing the square. We're kind of filling it out. And so we got the same solutions here, right, when it works out. And completing the square is easier to tell when you're in a situation where you might not get any solutions at all. It becomes pretty apparent even before you try to finish the process. Not all quadratics will factor. Like, if up here, like if we look at this one right here, if instead of minus 15 that were minus 14, like I make a really small change, I don't think that'll factor, right? So like solving by factoring is actually a really nice technique that works on some quadratics. Completing the square works always. And so that's what we're going to do on Tuesday after we take our test on Thursday. Are there questions on what we did so far today? Okay. All right. So then we can use the rest of the time for you to either work on the problem set or your assigned problem to get points back on test 2. That problem is due today if you're going to do it. Feel free to work together on the problem set or your assigned problem. I'll float around and answer questions as you have them.
Thank you.